The input into the machine learning system is very known. So it's like an array of values that can come from a set of sensors, and you know the output of those sensors.
Hey guys, welcome to Embedded Toolbox, the video interview series where we try to save the world by solving one engineering challenge at a time. And we're back with episode 4 of Let's Build a Robot. And joining us today is Mihai Dragusu, who's a member of the technical staff over at Wind River. How you doing, Mihai?
Hey, okay.
Very good. So we're going to need some artificial intelligence in this application. Most notably, we're going to need computer vision. Now, before we dive into the ins and outs of the computer vision, one of the big issues when you're using artificial intelligence in an intelligent yet deterministic system like a robot is the fact that the robot system itself needs to be maybe safety certified, but certainly deterministic if it's going to be mobile. AI by its very nature oftentimes isn't. So what can you say about the use of any potential redundancies that are going to be needed, or just in general, what you have to do from a technology standpoint?
You can have control systems that model a physical setup, and you can have neural networks actually controlling that system. However, in that case, this mostly applies to industrial cases. The input into the machine learning system is very known. So it's like an array of values that can come from a set of sensors, and you know the output of those sensors. So all the possible combinations and outputs are already modeled and engineered in. The only redundancy is that you can have there, or fail-safe is just to come back to the quality of the sensor actually, rather than the machine learning part. And of course, there are other cases, especially in the computer vision part of machine learning, where, as you said, things are not so deterministic. And the way I see that is, it's better, you can use it in solutions that are better than nothing. So basically think of pedestrian detection and system that like the emergency assist in a vehicle, emergency brake assist in a vehicle, right? That doesn't stop your car.
One of the last major components of our robotic system build on this Let's Build a Robot Embedded Toolbox is OpenCV. So OpenCV is obviously really popular as far as computer vision goes. It may be the most popular framework out there today. Can you explain what OpenCV is in your words, and what's going to be needed to get us going with that in this design?
So OpenCV, it's, as you said, very popular computer vision framework. It has so many modules right now that you cannot really describe it just as computer vision. So you can do a lot of matrix and array processing using its tools. It has ways, especially for small devices, it has a way to ingest machine learning models that were trained in big frameworks like TensorFlow or PyTorch, and basically you can use those outputs, the models, with OpenCV to do the inference part on it. So you don't have to port heavy-duty machine learning frameworks in embedded devices that can cost you a lot in time and effort.
Very good. Well, you've got a demonstration queued up for us today and help us accelerate our intelligent system build. Do you want to share your screen and jump right in?
Yep, sure. So I have this robot. This is the TurtleBot. I can zoom in a bit with it. So this is the TurtleBot 3. It has a Raspberry Pi 4 board on it. I think you can buy it with 3, 4 things like that, but mostly it's Raspberry Pis and Raspberry Pi clones. It has the LiDAR, right? And afterwards, I'm going to show you how to connect a gamepad to it, so we control this robot with the gamepad, and also a camera, so that we can do some computer vision stuff on the robot. So this assumes that you already have VxWorks booting on it according to the steps from our last videos. You have ROS tool built and deployed on it. So I'm going to take it from there, right? So what I have set up here is the thing is booted. And I also started a FTP server with Python. You can get this from PyFTP lib on GitHub, and you just basically get this directory copied in the regular site packages directory that all the Python modules sit on. And afterwards, you have something like this script that starts your FTP server, and this just helps you do the whole developer cycle, like build, test, deploy faster, right? All of this, even the script, we're gonna be sharing them on Lab, so everyone will have access to them.
Great.
Okay. So with this started, you can do things like just connect it, right? And now we have access to the file system on our robot. It should look basically like this, right? Nothing special. All our binaries go here. It's just, you can copy them everywhere just for to be a bit organized. I put them in user bin, right? Okay, so that's just the setup for the robot part. As for the building of the tools, I have here a container that is used to build ROS tool in. And inside this container, we can also you can also use this container to build our applications. What I did more for this part is I mounted my applications inside this container, right? So we have them here. And you just go like this. You source the environment for the Wind River VxWorks SDK, and you source the environment for the ROS to build. And right now, we can go to a directory where we have our application. This application looks like this. So it's basically a ROS package, right? So it's this one, right? And with the ROS package, is nothing too special about it. It's a CMake project where you also build this file. It's a very specific to ROS. You add a name, a few dependencies. This can get you, will provide you a model to build more complicated setups. And of course, the CMake file that builds it, it's again has a lot of ROS2 specific things, but at the same time, you can add your sources, and that's about it. And the application is almost exactly the same like the basic teleoperation demo that you can find everywhere for ROS2, with the added bonus of having gamepad and keyboard support for the VxWorks part, right? This come included. All that support come included with the package. As I said, we'll provide them, so you don't have to worry about those. And the rest of the code is basically the same as any teleop demo, right? We also have an obstacle avoidance application that is copy paste from the previous one with the added processing of the LiDAR sensor output, right? So this is a very basic algorithm that is like nothing too special. You just turn around when there's more things on the left as opposed to the right, right? And all of it is mostly the same. So this is the code. What you do to build this code is after you've sourced your environment and go to the specific directory, you just write cmake and then make, and then you're done. That's it. This C3 control executable is something that's built for VxWorks. This is going to run on our robot. All we have to do right now is basically copy it over from our build environment to the robot. So I've already done that. I don't need to go through the steps. We can find it here, right? And that's about it. We can do the same thing for the obstacle avoidance, is exactly the same steps. One more cool thing about our SDKs, probably have mentioned in previous videos, you can build DKMs, downloadable kernel modules. So until we started building this, we started playing around with this robot, we didn't have a gamepad driver. So one of our colleagues was keen enough to build one for us, right? So we have it right here. It has like all the code that you would find on a driver, but it also is built with the SDK, so you don't need to have access to the VxWorks sources. You can build it against the SDK. The CMake file is really that simple, is the most basic CMake file you can get, with the added option of -DKM here, so that you can tell the compiler that it's going to be for the kernel and not for the user space. And that's it. With all of those done, you can go build your gamepad driver, just like we did the previous application, cmake, make, and it's done. All you have to do is copy it over and load it when the time is ready. So that's for the robot application building part. We've talked that we're going to use OpenCV, and you're going to see that that's not much different from what I've shown you. You can go and get OpenCV from Wind River Labs GitHub. And here you'll find a very in-depth README that will provide you all of the details to build it and customize it if you need to. I'm just going to show you how I build it for this case. So it's still, if you didn't already set up the SDK environment, you have to. I already done that, so I don't have to. And then all you need to do is go to somewhere where you've already cloned the sources. So let's see, we have it here, right? Okay, you make a directory build as you would with any normal CV, OpenCV platform. Right, you go into that directory and you run this cmake. Oh, sorry, it just went straight through the building part. So you run this cmake command. What this really does is just telling the cmake build that we have a special toolchain file where all of the options tailored for VxWorks are placed in. This come with the OpenCV repository that we have. You tell it an install directory so that we can copy all of those files from the install directory onto a robot. And this is just a precautionary thing specifying the Python executable, because in our Docker environment, I had some issues with detecting Python correctly. So that's load. And then is the source directory like you would on any OpenCV build. This will take a while to pass through all the OpenCV configurations. As you can see, we're going to be building most of the OpenCV modules. More importantly, we have the DNN one that I was telling you about that can load TensorFlow models or PyTorch models and things like that. And what you do from here is just type make, and it's going to build. If I do this right now, it's going to take a while. I've already done that. So we already have the install files. They look like, let's see here. They look like this, right? So it's a basic Linux-like structure. And all you have to do is copy this user directory over into your robot. And then you have OpenCV support, and that's about it.
That's great.
Right. Yeah. But that doesn't stop here. You can also make like a merger project between ROS and OpenCV, because as I said, yeah, you have the capabilities to do machine learning with this setup. However, it does not really make sense for us to use a machine learning, a heavy-duty machine learning model on our poor Raspberry Pi here. It will not handle that, right? So one thing that's being done right now quite often is you have a small device, it can capture images, it can process them a bit, but then it sends them over to a machine that can do the machine learning part better for them. Sometimes that machine is right next to it, so they are tightly connected, you have low latency between them, and you can do things fast. Other times it's in the cloud, because you don't need that response so quickly, right? In our case, it's going to be my development machine, so we will have some quite good frame per second here. Okay, so what I've done to set up all of that, you just need to go to the ROS2 demos repository. And what we're interested in is this image tools project that basically captures images from our device. It sends them over using ROS2 messages. And on the other side, we'll have mirror services that will capture those messages and process them. Where OpenCV comes in is the fact that this project is dependent on both ROS to send the images over and OpenCV to capture them. Mm-hmm. So what you need to do for that, you just go to this GitHub repo and clone the demos. And for VxWorks, you do the same thing. You source the SDK environment, you source the ROS2 environment, right? You go to the place where you have that image tool thing, and the same as most of our, examples here. You go to CMake. What we do here is point this project to where our OpenCV libraries are so that it can link with them, right? And that's about it. We run CMake and then make. And what we have right here is this cam to image that will be an image publisher for our images to go to the other machine. Okay, so this is like a two-part setup. We have this. This will send the images over. We need the second part to capture them and process them, right? And basically, you need to do the same thing with this image tool project, but for Linux. And what I have right here is a Docker container that has ROS 2 installed for Linux this time. So we have all the environment set up already. And it has also OpenCV for Linux installed, and we only need to go to this demo repository and build it. You can build it as shown you a CMake way to build this project. There is also a, let's call it ROS way to build it using the callcon thing. It does exactly the same thing and it builds the tool for us. So now we have the other side of the environment setup. And that's mostly it. That's all you have to do to have your environment ready to do some fun things with the robot.
Great. So right now, we've got the entire system configured so that when we move into actually capturing data with the actual robot in the next episode, we're going to be able to talk back to your development environment and pull information that's being captured and then obviously compute it. In the real world, obviously, you mentioned sometimes that's not going to be possible at extremely low latency or with a PC sitting right next to it. What happens in those instances? Are you storing a lot of that data locally and then, say that you're communicating over a 5G network and then just holding it until you can shoot it back to the cloud or maybe some on-prem server, or how would that work?
So here it mostly depends on the latency requirements for that specific project. So you have things arraying from, very small sensors that sit in a tree in a park somewhere that gather data, and from time to time they can connect to something, send the data to the cloud, they get analyzed, you get some sort of predictions from that and stuff like that. But there are other cases where you need that in deployment low latency setup. So I've actually taken part in a few presentations where I saw some quite interesting devices. There are like this big ruggedized PCs that had 4 GPUs in them. And they are supposed to be like something for military use cases where you have someone actually carrying that thing around so that the drones or whatever other small devices they have around that processor, they can leverage that compute power near them.
Wow.
So it really depends on the how much you need that performance.
As far as the whole, oh no, I don't want to have to work with an RTOS, I don't know anything about real time, it appears that most, if not all of that's abstracted away from those engineers.
For the application development side of things, if you want to try it out, that's kind of the point with our program with labs, is to get people interested and setting up things like Raspberry Pis and various personal projects just to get things going, not to dive right into the hard stuff with real time.
That's great. So today we set up the entire environment to get ready to start capturing things with OpenCV and coming up with some results, with some outputs. Next time we're actually going to look at this in action. Isn't that right, Mihai?
Yep.